Newton's second law can also be used to develop a relationship between the force of gravity, which is Fg, and the acceleration due to gravity, which is little g. When I look at Newton's second law, it's F net equals ma. For an object in free fall, nothing is touching the object because we ignore air resistance, and we know that its acceleration is equal to negative 9.80 meters per second squared, or little g. So Newton's second law becomes Fg equals mg. When I look at that equation, what I'm really finding is the weight of the object. Fg refers to the weight. Sometimes you will see it written as Fw. I may do that sometimes in class because I'm used to using Fw, but because our textbook uses Fg, I'm going to try to stick to that. So Fg refers to the weight. The weight of an object is measured in newtons. Newton is the unit for all forces. A newton is a kilogram times a meter per second squared. The weight of an object, as you can see in the equation, Fg equals mg, depends on the mass, but also the acceleration due to gravity at your location. So your weight, or the gravitational force on your body, which is Fg, is going to change if you were to go to the moon. Mass, however, is a property of an object that does not change. It is measured in kilograms, and it will stay the same whether you're here or you're on the moon. One of the ways that we typically measure weight is to use a scale. And when we use a scale, what we are looking at is a free body diagram where Fg is the downward force, and most scales use springs, so we'll call this the spring force. So if I were to sum the forces, F spring is my upward, minus Fg is my downward, that is equal to my F net, and we know that F net equals mass times acceleration. So if I want to get the reading on the scale, which we'll just call the spring, the force of the spring, because when you stand on a scale, obviously the earth is pulling you downward, but there has to be something pushing back up. That's the springs on the scale. So if I rearrange this equation to be ma plus Fg, when you're standing on a scale in your bathroom, you're not accelerating. So my ma becomes 0 because of the zero product property. Whatever I multiply by a, which is 0, I get a 0 answer. So a scale typically reads your actual weight. So when you're standing on a scale, it's reading that force that opposes the force of gravity on your body, which we typically call the spring force. We will be using spring scales this year. Some of the scales in your home would be using springs. So we typically call that the spring force. However, what if the scale itself is accelerating? So if I take my equation, the spring force, which is the reading on the scale, is equal to ma plus Fg, then I could see how a scale could read something that is not my weight. So you're going to ask, how do you make a scale accelerate? One of the ways to do that is to put it in an elevator. And you're going to see some elevator questions in the sublevels. If I'm riding an elevator, whether it's moving up or it's moving down, at certain points in the ride, it's going to accelerate. If I have a positive acceleration, that means that the reading on the scale will be greater than your actual weight. If the acceleration is negative, that means that the reading on the scale will be less than your actual weight. So we're going to do a lab where you actually get on an elevator, and using a spring scale, you measure the weight of an object. It's just going to be a 1 kilogram mass. When we get a reading on a scale that is different than the actual weight of the object, we call that the apparent weight. So when we are measuring the weight of an object, we are actually not measuring the weight directly when we use a scale. We're measuring the upward force that opposes the weight. And as I said, when you're in your house, you're not accelerating. So that would be your actual weight. But if you put your scale on an elevator, you're going to see, because the elevator is accelerating, that there are points in the elevator ride when the scale reads either greater or less than your actual weight. So that brings about another question. If I'm riding in an elevator and the elevator cable breaks, what's the scale going to read? If a breaking cable, which is what holds the elevator up, would cause the upward force to disappear, if a scale reads the upward force, then the scale is going to read 0. So when you hear the term weightless, it doesn't actually mean that the object has a weight of 0. It just means that its apparent weight is 0. Because if you were in the elevator on that scale, and the top cable broke, there's no force there any longer. You're just in free fall. And in free fall, we remember that the only force acting on it is gravity. So that upward force would be 0. It does not mean that you've all of a sudden become weightless. It simply means that your apparent weight is 0. Since we're talking about the acceleration due to gravity, let's take a look at free fall and again at air resistance. We know from last chapter that all objects, regardless of their mass, fall at the same rate. This is known as the acceleration due to gravity, and it's negative 9.8 meters per second squared. We always ignore air resistance in our problems, but that poses the question, what if we didn't ignore air resistance? When we look at the difference between an elephant and then I think that's a mouse, elephant has a much greater weight, or the force of gravity. It's 10,000 newtons approximately. When I look at the force of gravity or the weight of a mouse, it's 10 newtons. So they have very different weights or very different forces of gravity. But their masses are also very different. The elephant is 1,000 kilograms. The mouse is only 1 kilogram. So their acceleration is the same. Even though their forces are different, because their masses are different, their acceleration is the same. So when I look at the difference between an elephant and a feather, and what effect air resistance will have on falling objects, there are 3 things that determine air resistance. And air resistance is just a contact force that results in the collision between the air and the object. The first one is air density. Okay? Density refers to the amount of particles in a certain volume. So it makes sense that if the air is more dense, there's going to be more drag or more air resistance. We often refer to air resistance as drag. The cross-sectional area of the object. If you see somebody skydiving and they're wearing one of those squirrel suits, if they spread their whole body out like a starfish, they're going to have more area, which gives more air resistance. If they combine up and roll into a ball, there's going to be less air resistance. And the last thing that affects air resistance is the speed of the object. As an object is falling, it's speeding up. Its velocity is increasing. As the speed of an object is greater, the air drag also increases. So if I increase air density, increase cross-sectional area, and increase the speed of the object, that's going to increase the air resistance. So what will happen to an object is because the drag changes, it would continue to increase as you speed up, and we already know that as I fall, free fall, I increase in speed. That's going to increase my drag until there's a point, just like you can see in the animation, where the drag, as it becomes larger and larger and larger, is going to equal the weight of the object, or the gravitational force. When that happens, the object reaches terminal velocity. What that means is that the change in velocity terminates. In other words, it stops accelerating. And we call that velocity the terminal velocity. So if we include air resistance, our problems become a little bit more complicated. We know that air resistance will slow an object down. So its acceleration, although it starts at negative 9.8 when it's in free fall, will decrease and decrease and decrease as that air drag increases until we reach a terminal velocity. So those are just a few of the applications of Newton's laws that we will be developing in class.